You are listening to the alwaysasking.com podcast. This is episode number 2. Today's question: are we alone? The universe is a big place. But then, where is everyone? Today we will use the best available scientific evidence to review the possible answers to this question. Enjoy.
Are we alone? Might Earth be the sole exception to an otherwise dead universe? We shouldn't be. The ingredients for life are everywhere. Life should be common. But then, where is everyone? This article explains the 3 possible answers to this question. By the time you finish reading, you will have a firm grasp of the relevant science, enough to form an opinion on which answer is probably right. Requirements of life. To arise, life needs 3 things: matter, energy, and time. All can be found wherever there are stars. Each star is like a scratch-off lottery ticket, a chance to win by having the right combination. The prize: the universe gains a new planet full of life. The chance a ticket pays off remains unknown, but science has made progress in estimating the odds. Given the huge number of tickets, there are 10 to the power of 22 stars in the observable universe. The chances seem good that more than one has paid off. Let's review the specific requirements life has for matter, energy and time. Matter. Matter is the stuff life is made of, the building blocks. These are the chemical elements: hydrogen, oxygen, carbon, nitrogen, and so on. These elements exist everywhere. They're created as byproducts of fusion, the ash of nuclear fires which burn in every star. Quote: the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. End quote. Carl Sagan. Hydrogen, oxygen, carbon, and nitrogen make up over 99% of the atoms in our bodies. The others are needed only in trace amounts. These same 4 elements that compose the bulk of our bodies are also the most common chemically active elements in the solar system. The same physics and chemistry that operate here apply everywhere in the universe. The familiar elements on Earth are found in every star and galaxy we see. This is more than conjecture. Through analysis of light, astronomers can determine the chemical composition of faraway stars, nebulae, and galaxies. Complex organic, carbon-containing molecules, the precursors to life including amino acids, have been detected in distant star-forming gas clouds, or stellar nurseries near the center of the galaxy. So you are made of the same stuff as stars, planets, comets and gas clouds. Given the availability of these vital ingredients, the whole universe is filled with the matter needed for life. But life still needs energy, and enough time to evolve. Energy. All life feeds on energy. Energy forestalls the natural tendency towards disorder. Anytime order is created, such as in growing a body, energy must be expended. Plants obtain energy from sunlight and store it in chemical bonds. Animals get energy from plants, by eating them and breaking those bonds to release energy, or they eat other animals. The energy that drives the entire food chain and powers all living things on Earth started in the core of our Sun. The same fusion responsible for cooking the chemicals of life provides stars, and life, their energy. Though all life needs energy, not every life form gets it from sunlight. Europa, one of Jupiter's moons, appears on the surface to be a frozen ball of ice. But scientists believe that 10 miles under its frozen surface lies an ocean with twice the liquid water of Earth's oceans. What provides the energy to melt this ice? The tides? Tidal friction creates heat that could melt the ice and provide energy for life. Ultimately, this energy comes from the spinning of Jupiter. As Europa's own tidal forces drag on Jupiter, Jupiter's rotation slows and its days become longer. The oldest known life forms used geothermal, rather than solar energy. They got their energy from hydrothermal vents like the Lost City undersea geysers powered by the heat of Earth's interior. Life uses energy wherever it finds it. In 2017, researchers discovered fossilized hematite tubes that are 4.28 billion years old. This is the oldest evidence for life known. In comparison, Earth is 4.54 billion years old and its oceans, 4.41 billion years. Once conditions permitted, it didn't take long for life to start. Time. The final requirement for life is time for life to arise and evolve. After the formation of Earth, it took a few 100 million years for life to appear. Several billion more were needed to evolve multicellular life. It took a total of 4.3 billion years to get to mammals, and 4.5 billion to yield a tool-making civilization. To progress through these stages required an environment that remains stable for long periods. The large stars exhaust their nuclear fuel and explode or collapse after millions of years. This time is too short to host planets with complex life. But in their demise they give hope to others. The elements baked in their cores is what enables life in other star systems. This explains why life could not appear much earlier in the universe's history. Several generations of large stars had to form, live, die, and explode to spread their ash, the stuff of life, into interstellar space. Smaller stars are needed to tend to a life-bearing planet. They offer sufficient time for life to do its thing. The lifespan of a star depends on its mass. The smaller its size, the longer it lives. Medium-sized stars like our Sun last for billions of years. Smaller stars, like red dwarfs, can live for trillions. Time is one thing the universe is not in short supply of. But life also needs stability. For a planet to nurture life, it must provide stability. It needs a stable orbit, and a host star with a consistent brightness. The planet must also avoid potentially life-ending calamities, asteroid impacts, supervolcanoes, and gamma-ray bursts. Earth has had her own share of catastrophes. The Moon is thought to have formed when Earth collided with a Mars-sized planet called Theia. It's also believed that at one time the entire surface of Earth was covered in ice. Despite these, and many asteroid impacts and supervolcanoes, once it got started, life has held on. Life's tenacity. Life has been found as deep as 19 kilometers underground, 77 kilometers up in the atmosphere, in lakes under the ice of Antarctica, and in the scalding 80 degrees Celsius pools of Yellowstone. Where life can exist, it will. Rapidity of life. Life took hold nearly as soon as conditions permitted. Of Earth's 4.54 billion year history, 94% of that time it's been home to life. Quote: if life arose relatively quickly on Earth, then it could be common in the universe. End quote. Stephen Blair Hedges. Despite many attempts by nature to kill it off, life hasn't let go since it took hold. Life is hardy. Extremophiles. As an indication of the extreme conditions life might tolerate on other planets, biologists on Earth have taken particular interest in extremophiles, creatures that can survive under extreme conditions. The bacillus bacteria has been found to survive temperatures of 420 degrees Celsius, 788 degrees Fahrenheit, and have been revived from a dormant state after 10,000 years. One report even claims to have revived it after being locked in a piece of amber for 25 million years. Perhaps the most resilient species on Earth is the tardigrade, also known as water bears. They're about 1 millimeter long and look like tiny 8-legged hippos. They can be found almost anywhere. Water bears live mainly in fresh water and moss, but have been found on the tops of mountains, at the bottom of the sea, in hot springs and rain forests, and even in the icy Antarctic. They can survive ionizing radiation, dehydration, starvation, being chilled to near absolute zero and heated to over 150 degrees Celsius. Tardigrades can tolerate exposure to the vacuum of space as well as pressures 600 times that of Earth's atmosphere. They can put themselves in suspended animation and reanimate a century later. The European Space Agency sent water bears to space to be exposed to solar radiation, cosmic rays, and the vacuum. 2/3 survived. Some of the females even laid healthy eggs while in space. If creatures can be so tough as to survive in space without suits, could they hitch rides to other worlds? Panspermia. A theory called panspermia proposes that it's not just the elements of life that are spread throughout space, but the seeds of life itself, primitive organisms that can survive trips through space and colonize suitable worlds they land on. It sounds outlandish, but there are indications it's possible. Though no mission to Mars has ever returned with a sample of Martian rocks, you can see a rock from Mars at the London Natural History Museum. In fact, to date over 266 Martian rocks have been found on Earth. How did they get here? These rocks were blasted into space by impact events on the surface of Mars. Once in space they floated for unknown amounts of time before getting caught in Earth's gravity, and falling to the surface. Mars had oceans before Earth. Some scientists believe life began on Mars. If life began on Mars, it is possible that it hitched a ride to Earth on a Martian meteorite. In 1996, NASA scientists found evidence of fossilized microbes in a Martian meteorite. The meteorite was discovered in the Allen Hills of Antarctica in 1984, giving it the designation, Allen Hills 84001. Quote: Today, Rock 84001 speaks to us across all those billions of years and millions of miles. It speaks of the possibility of life. If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered. Its implications are as far-reaching and awe-inspiring as can be imagined. Even as it promises answers to some of our oldest questions, it poses still others even more fundamental. End quote. President Bill Clinton. But the evidence was speculative. It was based on nothing more than microscopic bacteria-like shapes found in the rock. The scientific community did not accept this as definitive evidence of life on Mars. But in 2019, Hungarian scientists studying another meteorite of the same region, Allen Hills 77005, had a significant finding. It turned out these bacteria-like shapes not only had similar forms and size to bacteria, but chemical analysis revealed mineralized organic compounds, chemicals we would expect to find if these shapes are indeed the fossilized remains of once living cells. If the first life did arrive here on a meteorite, we're not Earthlings but Martians. Though life may have started on Mars, complex life could not arise there. Mars's feeble gravity couldn't hold onto her ocean or thick atmosphere. As they leaked into space, Mars became progressively colder and drier. This fact demonstrates the equally important requirement of time. Earth's oceans are destined to suffer a similar fate. But not for another 1.1 billion years. In April 2019, the Bereshit lunar lander, a privately funded project, accidentally crashed on the Moon. Among its cargo was a sample of water bears, who are believed to have survived. Quote: We believe the chances of survival for the tardigrades are extremely high. End quote. Nova Spivak. So there is life on other worlds. It came from Earth and it's now on the Moon, panspermia in action. The Fermi Paradox. Enrico Fermi is the architect of the nuclear age. He built the first nuclear reactor by arranging tons of uranium and graphite in a massive pile in downtown Chicago. The reactor was built in secret in an abandoned racket court under Stagg Field at the University of Chicago. The undertaking was top secret, part of the Manhattan Project. Despite the dangers of building a reactor in a densely populated area, project leaders trusted Fermi's calculations. In the summer of 1950, Fermi made a visit to the Los Alamos Scientific Laboratory. At the time, Edward Teller and others were working on the fusion bomb, a bomb that would release the energy of the stars on Earth. During a casual lunch with fellow nuclear scientists Edward Teller, Herbert York, and Emil Konopinski, Fermi blurted, "But where is everybody?" Quote. The result of his question was general laughter because of the strange fact that in spite of Fermi's question coming from the clear blue, everybody around the table seemed to understand at once that he was talking about extraterrestrial life. End quote. Edward Teller. In the ensuing conversation, Fermi did some rough calculations. He estimated the number of stars, the fraction of stars with planets, the fraction of those planets the right distance from their star, and so on, to arrive at a rough approximation of the number of planets with life. The number he arrived at was so great Fermi concluded we should have been visited many times over. Here was a contradiction. On one hand, the calculations say we should have been visited. On the other hand, the lack of evidence suggests we haven't. This contradiction is the Fermi Paradox. The Drake equation. In 1961, the astrophysicist Frank Drake formalized Fermi's estimations in the Drake equation. It is a simple formula. It simply multiplies together 7 values to provide a final estimate for n, the number of presently detectable alien civilizations in our galaxy. N equals R times F sub P times N sub E times F sub L times F sub I times F sub C times L. Each of the 7 numbers is a parameter whose estimate can be refined over time as new data comes in. The parameters span distinct areas of human knowledge, including astrophysics, biology, evolution, anthropology, and technology. As our knowledge concerning these parameters improves, so too does our estimate for n. A pattern that one quickly notices from playing with the equation is how difficult it is to get the number of predicted civilizations in the universe down to 1. It requires what seem to be insanely conservative estimates for the parameters. This is a reflection of the sheer quantity of stars in the observable universe. There are some 100 billion stars in our galaxy, and there are about 100 billion visible galaxies. This amounts to 10 to the power of 22 stars. Could Earth be the only civilization in the observable universe? This requires the probability of a star system producing intelligent life be extremely low, on the order of 1 out of 10 to the power of 22. That's 1 in 10 billion trillion, or 1 followed by 22 zeros. To appreciate the magnitude of this number, it helps to see it written out, 1 in 10 sextillion. Even if life is very rare, so long as it is not incredibly rare, the universe ought to be teeming with it. Quote, 1 in 10 billion trillion is incredibly small. To me, this implies that other intelligent, technology-producing species very likely have evolved before us. Think of it this way. Before our result, you'd be considered a pessimist if you imagined the probability of evolving a civilization on a habitable planet were, say, 1 in a trillion. But even that guess, 1 chance in a trillion, implies that what has happened here on Earth with humanity has in fact happened about 10 billion other times over cosmic history. End quote. Frank Drake. To imagine just how many stars there are, try to imagine all the grains of sand on a beach. 1 handful of sand contains about 10,000 grains. More than the few thousand stars you might see in a perfectly dark sky. Yet the total number of stars in the observable universe exceeds all the grains of sand on all of Earth's beaches. You would need 10,000 Earths to have as many sand grains as there are stars. How likely is it that of all these grains, only one is blessed with life? Our search for ET. Today there are 4 tracks in our The Search for Extraterrestrial Life. 1. Listening for intelligent signals. 2. Looking for habitable planets. 3. Searching for alien artifacts. And 4. Sending our friendly greetings. Listening for signals. The search for extraterrestrial intelligence, SETI, began in earnest in 1984. Frank Drake was one of the SETI Institute's first leaders. The mission of SETI is to understand the origin of life, and the evolution of intelligence. SETI employs a network of radio telescopes to comb the sky for transmissions by technological civilizations. To date, SETI has scanned only a minuscule fraction of the sky. So far, there have been no confirmed detections of alien signals. Though, one detected signal defies all explanation. In 1977, Dr. Jerry Eman was a volunteer at SETI. One day, he looked over data collected from the Big Ear radio telescope a few days prior. The telescope was listening in the direction of the Sagittarius constellation. It was then that Eman noticed something that astonished him and his colleagues. Quote, "I came across the strangest signal I had ever seen, and immediately scribbled wow next to it. At first, I thought it was an Earth signal reflected from space debris, but after I studied it further, I found that couldn't be the case." End quote. Jerry Eman. The event is known as the WOW signal. Nothing like it has ever been observed since. The WOW signal is surprising on many levels. No known astronomical phenomenon produces a signal like what was seen. The signal was strong and clear, many times stronger than the background noise. The signal was at 1420 MHz, the exact frequency astronomers expect ET to use, and in a frequency range where international law prohibits transmissions. 1427 MHz is restricted. The signal's Doppler shift indicated it came from a fixed point in the sky not moving with the Earth or solar system. This rules out any spacecraft, aircraft or terrestrial origin. NASA confirmed there were no space probes in the direction of the sky at the time. The direction of the signal was 90 degrees off from any planet including Pluto. Despite hundreds of attempts to detect the signal again, it was never seen since. The Big Ear telescope points in a fixed direction and only sweeps across the sky as the Earth spins. Accordingly, the Big Ear telescope was only able to hear the WOW signal for 72 seconds. These 72 seconds represent the only concrete evidence we have of extraterrestrial intelligence, and it's far from conclusive. But we don't have to wait for alien life to make the first move. We can go out and look for it. Looking for planets. When the moon crosses between the Earth and Sun, the result is a solar eclipse. During such an eclipse, the sky darkens as the moon's shadow crosses over the Earth. But the moon is not the only body that can create an eclipse. Eclipses that don't fully block out the sun are known as transits. This is when we see an astronomical body, such as Mercury or Venus, cross the disk of the sun. Whenever a body crosses between Earth and the sun, the result is an apparent dimming. Less light makes it to Earth as a result of it being blocked by that body, be it the Moon, Venus or Mercury. Astronomers realized this dimming effect could reveal planets in faraway star systems. Finding habitable planets. The Kepler Space Telescope remained in service from 2009 to 2018. In that time, it monitored over 500,000 stars for periodic dimming, evidence of transiting planets. Based on the amount of dimming and how long it lasts, astronomers can determine both the size of the planet and the speed of its orbit. Using the laws of planetary motion formulated by Johannes Kepler, the speed a planet orbits its star depends on its distance from that star. Thus, the patterns of dimming of a star gives scientists enough data to know if there is a planet in the habitable zone of that star. The habitable zone, also called the Goldilocks zone, is a distance from a star that's not too hot, nor too cold, but just right. For instance, Earth sits sandwiched between blistering Venus and freezing Mars. The Kepler Space Telescope was a great success. Kepler discovered 2,662 planets beyond the solar system. Moreover, its data gives us better estimates for two parameters of the Drake equation. The fraction of stars with planets F sub p appears to be very close to 1. Kepler was also able to provide estimates for the number of environments n sub e suitable for life in each star systems. Kepler's data indicates at least 20% of star systems have a planet in the habitable zone. One habitable zone planet, K2-18b, is especially interesting. The planet was noticed by Kepler and found to be orbiting a star about 100 light-years away, close enough for Hubble to analyze the planet's atmosphere. In 2019, researchers determined the atmosphere contains water vapor, the first discovery of water on a planet beyond the solar system. The concentrations may even be high enough for the planet to have clouds. Given the success of Kepler, NASA moved to immediately replace it once the satellite ran out of fuel. In 2018, NASA launched a new and improved version of Kepler, called the Transiting Exoplanet Survey Satellite, TESS. TESS is able to monitor 400 times more sky than Kepler, and its greater sensitivity will allow it to detect even smaller planets on stars that are much closer to Earth. But a planet being in the right place isn't an indication it has life. A new experiment aims to correct that. Searching for signs of life. Just as astronomers detected organic molecules in remote regions of the galaxy, new experiments plan to analyze the atmospheres of exoplanets to look for biogenic gases. These are gases created by biological processes and, if observed, would be telltale signatures for the presence of life. No apparatus has yet been built with the required sensitivity to analyze atmospheres of planets beyond the solar system. But there is one device that will: the James Webb Telescope, the successor to Hubble. The James Webb Telescope may provide definitive proof for life beyond the solar system. But we won't know for some time. The telescope is scheduled for launch in March 2021. Searching for artifacts. If aliens have visited our solar system in the past, they may have left behind signs of their presence. When humans went to the moon, we left footprints, a flag, a plaque, even bags of feces. Absent interference, these signs might survive for eons. If humanity is not careful, they may even outlast us. If alien races perform engineering feats on planetary or stellar scales, if they leave behind probes, signaling stations or other artifacts, it is possible we may one day discover one. Von Neumann probes. In the 1940s, the polymath John von Neumann invented a machine that could reproduce itself. Crossing the idea of a self-reproducing machine with a space probe resulted in the idea of von Neumann probes, space probes that could stop in a star system to reproduce and then disperse outward in all directions to each of the next closest star systems. Such probes would only need a few million years to reach every star in the galaxy. This idea served as the basis of Arthur C. Clarke's short story The Sentinel, which itself was the basis of Stanley Kubrick's 2001, A Space Odyssey. In the story, humans discover that aliens passing through our star system eons ago left something behind, a token of their presence in the form of a beacon on the moon. As we turn our eyes toward the heavens, we may notice other, less subtle, clues of alien intelligence. Megastructures. Intelligence and technology gave us the power to alter our environment. Some of our changes are visible from space. For instance, City lights cause parts of the Earth to glow at night. As our technology increases, so does our ability to change our environment. According to the Kardashev scale, present humans rank below a Type I civilization. Type I civilizations make use of all the energy resources available to a planet. The next stage according to this scale, is a Type II civilization, a civilization that makes use of all the energy output by their home star. This requires technology to build stellar engines. Stellar engines have been envisioned as large Dyson spheres or swarms of solar cells that orbit the star to capture large fractions of its energy output. Stellar engines would change the spectrum of the star in a very noticeable way, but none have been detected so far. Though Tabby's star has caught the imaginations of many. The strange behavior of Tabby's star was detected by the Kepler Space Telescope and reported by Tabitha Boyargin, who noticed irregular fluctuations in the star's brightness. The behavior remains unexplained. Sending our greetings. Perhaps aliens are shy. They might be waiting for us to make the first move, to signal our willingness to talk. Since the 1970s, humans have made several overtures to invite interstellar conversation. Broadcasts? In 1974, renovations on the giant Arecibo radio telescope in Puerto Rico completed. To mark the occasion, the powerful dish was used to broadcast a message to the stars. It is known as the Arecibo message. The message was written by Frank Drake with help from Carl Sagan and others. It is meant to be easily deciphered by anyone who might intercept it. It was encoded in binary, as a series of 1679 black and white pixels. When arranged in a grid of 73 rows by 23 columns, it forms a simple pictorial diagram. The message encodes a numbering scheme, the atomic numbers of the elements that compose our DNA, a picture of a person, and the radio antenna that broadcast the message. A telescope of an equivalent size and sensitivity to the Arecibo telescope on the receiving end could pick up the signal from a distance of tens of thousands of light-years, on the other side of the galaxy. Decades passed before any other deliberate attempt was made to speak to aliens. In 2012, the Arecibo telescope was once again used to send a message. This time it sent a reply to the part of the sky from which the WOW signal was detected 35 years earlier. The message consisted of 10,000 Twitter messages solicited by the National Geographic Channel. Who would have guessed that Twitter could be used to communicate with ET? Greeting cards. In 1977, the four outer planets Jupiter, Saturn, Uranus, and Neptune were aligned in a way that would not repeat until 2153. It provided the perfect opportunity to leave the solar system. NASA took advantage of the opportunity and launched two robots, the Voyager 1 and Voyager 2 space probes. On their way out, they were boosted by stealing a tiny bit of energy from each of the four gas giants, using a technique known as a gravitational slingshot. The speed is gained by falling in towards the planet, riding behind it as it orbits the Sun. The effect slows the orbit of the planet ever so slightly. The years for each of these four planets is now a bit longer. But in slowing down Jupiter, Saturn, Uranus, and Neptune, the speed of the Voyager probes was greatly boosted. It provided them with enough speed to break free of the Sun's gravity. Both probes are now free to roam the galaxy. It took over 4 decades, but as of 2018 both probes have left the solar system. Despite being over 20 billion kilometers away, we remain in contact with them via their 23-watt radio transmitters, surprising given that's only a few times stronger than a cell phone's 3-watt transmitter. Each of the probes contains a greeting card, in the form of a golden record. The records contain a selection of greetings in various languages, music, and sounds from nature. Quote, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts and our feelings. We are attempting to survive our time so we may live into yours." End quote. President Jimmy Carter. The records are made of copper and plated in gold. They're designed to last for billions of years. If the sun is to one day envelope the earth, these probes may constitute the only evidence humanity was ever here. Solutions to Fermi's paradox. Quote: "Two possibilities exist, either we are alone in the universe or we are not. Both are equally terrifying." End quote. Arthur C. Clarke. Thanks to Kepler, we can estimate there are 40 billion rocky planets in our galaxy with the right orbits to have liquid water. Despite this, science has yet to find solid evidence of alien life. Our galaxy is not filled with stellar engines, radio beacons, or self-replicating probes. Nor have little green men landed at the UN to establish an embassy. Our lack of evidence is not from lack of trying. How then do we square the idea that alien life should be common with the plain fact that we have yet to find any proof? There are many proposed answers to Fermi's paradox. But all fall loosely into one of three categories. 1. We are alone, life, or intelligent life is rare. It's either hard to evolve, or too fragile to maintain. 2. They isolate, aliens choose not to spread through the galaxy making noticeable changes to it. 3. They are here, aliens are here but they conceal their presence from us? Each of these possibilities is consistent with existing observations. To get an idea for which type of answer is most likely correct, we must review the proposed solutions in more detail. We are alone. Physically speaking, anything that can happen in one time or place can happen in another. All of science is based on this notion of reproducibility. Given the same starting conditions, the same outcomes result. If the universe is infinite, which by all indications it seems to be, then the possibility of life combined with an infinite extent of space statistically guarantees other life, including intelligent life, exists out there. But this doesn't tell us how near or far that life is. If intelligent life is so rare that it occurs on less than 1 star in 10 to the power of 22, then we might be the only example in the observable universe. The vast distances implied by being the only intelligence in the observable universe would, for all practical purposes, mean we are alone, even if infinite other intelligences exist across our infinite universe. Life is rare. The most obvious answer to Fermi's paradox is simply that he got his math wrong. He may have overlooked some great filter, something difficult to have, obtain, or pass, but is necessary for life. For example, it might be important, but also rare to have a large moon and a large planet like Jupiter nearby. Both help clear away and deflect debris in the inner solar system. This debris might otherwise plague Earth with perpetual planetary bombardment from asteroids, comets, and meteors. This idea is known as the rare Earth hypothesis. It is a proposed solution to the Fermi paradox. Other proposed rare coincidences relate to the fact that Earth has a fairly active interior. This interior both creates a protective magnetic shield and also makes for geothermal vents. These vents may have played a key role in kickstarting life. The hypothesized collision with Theia would be a relatively uncommon event. But it gave Earth her large moon. The moon creates tides, which create tide pools. Tide pools also might have played a role in the appearance of life. They provided a place for the chemical stuff of life to mix together and concentrate. The theory remains hotly debated. The counter-evidence for life being difficult is the speed at which it arose on Earth. It appeared relatively quickly, within a fraction of a billion years after Earth's oceans formed. The other argument is statistical. For Earth to be the only planet with life, life would have to be incredibly rare. It is conceivable that with a billion-year head start, an intelligent civilization 100 million light-years away could spread to us using von Neumann probes. For Earth to be the only planet with life for 100 million light-years, life would have to occur on less than 1 out of every 200 trillion star systems. More data will be required to settle the question of the rare Earth hypothesis. It may come within a few years, when results of surveys for biogenic gases are completed by the James Webb Telescope. It could also be disproved if conclusive evidence is found indicating primitive life on Mars, as suggested by chemical analysis of the bacteria-like shapes on the Allen Hills 77005 Martian meteorite. Intelligence is rare. According to this solution to the paradox, life may be common, but evolving complex intelligent life is not. This would explain why we haven't heard radio signals or found alien megastructures. Intelligence is a key factor in the success and survival of the human species. But for most of the millions of other species on this planet, it is not. Might we be biased in assuming evolution favors intelligence? Moreover, perhaps there are barriers to evolving through the various required stages. It may be that evolving multicellular life is difficult. After all, it took several billion years to get from single-celled organisms to animals. While evolving intelligence is not inevitable, there are reasons to believe intelligence is favored. The evidence for this is convergent evolution. Independent branches of the evolutionary tree separately evolved intelligence. Outside of our own primate lineage there are dolphins and elephants among mammals, grey parrots and crows among the birds, even the mollusks of octopuses and cuttlefish. Greater intelligence provides advantages to those species who evolve it. It enables predators to outthink their prey, and social creatures to outthink each other. Given that intelligence has arisen multiple times from different lines of evolution, it is reasonable to suspect that it will arise so long as life can bridge the gap from single-celled life to multicellular life. We are the first. Perhaps neither life, nor intelligence is inherently rare, we just happen to be the first. This theory is in line with the understanding that life should be common, and intelligence should be favored by evolution. It also explains the complete lack of observational evidence for other alien civilizations. However, the view that we are first runs counter to two facets of our cosmological understanding. The first is that life could have arisen billions of years earlier than it did on Earth. Rocky planets formed in the first billion years after the Big Bang, and carbon was abundant after 1.5 billion years. We know carbon and other necessary elements were available then by looking at old faraway galaxies. It's estimated that the first intelligent civilizations existed as early as 5 billion years ago. Given the rate of formation and destruction of stars systems, the average extraterrestrial civilization has a 1.7 billion year head start on us. In the words of Carl Sagan, we're Johnny-come-latelys. The second cosmological idea this runs counter to is the Copernican principle. The Copernican principle says we should not expect to hold any privileged position in the universe. Statistically, it's far more likely that we occupy some average or middle position, than hold a special spot like being first. If billions of civilizations are expected to live in this universe, the odds that we're the first would correspondingly be 1 in billions. Intelligence destroys itself. In a twist of fate, perhaps Fermi's own work provides the very answer to his question. Fermi ushered in the nuclear age, paving the way to technologies that could bring about our destruction. What's more scary, is that nuclear weapons are just the first of many technologies that carry such a burden. We now contend with the risks from biological weapons, AI, nanotechnology, and environmental destruction. Some even fear that modern physics experiments, like particle accelerators, pose an existential risk, though this particular threat is low given that higher energy collisions occur naturally. As doomsday technology becomes more broadly available, an ever-increasing number of hands will hover over big red buttons. It is an unstable situation. Even if there's just a 1% chance per year that one of these technologies wipes us out, that means humanity has less than a 5% chance of surviving the next 300 years. If we're not careful, we could spell our own doom. But even if many, or most intelligent species wipe themselves out, it seems unlikely that all of them do. Some should survive to inherit the stars. Quote, "A single message from space will show that it is possible to live through technological adolescence." End quote. Carl Sagan. Humanity has so far managed to survive perils of our making. It's incumbent on us to keep it that way. They isolate? If intelligence exists throughout the universe, we haven't noticed. But rather than assume this is because nothing is out there, it could also be that we're not looking in the right places or for the right things. We expect aliens to conquer the universe, transforming it in their wake, but perhaps they choose to keep to themselves where they might explore the limitless depths of inner space. They are quiet. The search for SETI-assumed radio transmission will be how alien species communicate. We expect alien civilizations to be noisy in the radio spectrum, filling the airwaves with their music and television. But SETI is a reflection of our 1970s technology, a time when TV and radio broadcasts were the primary means of distributing information. Since then, we've largely shifted away from broadcast TV to closed-circuit and point-to-point systems, cable TV, fiber optics, satellite dishes, and internet streaming services. These technologies offer more channels and data transmission. They're also quiet. An alien civilization would be unable to intercept what you watch over Netflix. Though we still use radio, technologies are moving away from central broadcasts towards localized low-power systems, like cellular networks. Spread-spectrum technologies increase the reliability and bandwidth of our transmissions, but also make them harder for outsiders to differentiate from background noise. Even if civilizations last for millions or billions of years, the window during which they transmit openly into space with high-power radios might last only a few decades. Lasers enable more efficient and higher throughput communication, but only recently has anyone started to look for alien laser transmissions. What about the lack of alien megastructures, like Dyson swarms? It turns out even the technology of our science fiction is far behind the possible technology of alien civilizations. Building a Dyson swarm around a star requires vast amounts of matter and energy. Entire planets would need to be disassembled to provide the raw materials. In the end, the Dyson swarm would capture only 0.7% of the energy present in the mass energy of the star, and it would take the entire lifetime of the star to capture. An advanced civilization could much more easily construct a black hole engine. Such an engine can turn 100% of mass into energy, 142 times the efficiency of fusion. Moreover, anything you feed it is fuel. Just drop something into it and the black hole turns it into pure energy in the form of Hawking radiation. Quote, "A mountain-sized black hole would give off X-rays and gamma rays, at a rate of about 10 million megawatts, enough to power the world's electricity supply." End quote. Stephen Hawking. A civilization using micro-black holes to meet its energy needs would be very difficult to detect. Black hole engines were inconceivable before 1974 when Hawking proved black holes radiate. The technologies available to civilizations millions of years ahead of us may be less fathomable than a black hole engine would be to an ancient Babylonian. We still don't even have a good understanding of gravity. Space is too big. Space is big. So big that many believe interstellar travel is so resource and time intensive that no intelligent civilization would seriously bother with it. This would account for why we haven't been visited. Take, for example, the fastest thing humans have ever launched, the the Voyager space probes. Voyager 1 is traveling at 61,200 km per hour, 17 km per second. Despite this speed, it will take Voyager 40,000 years to even approach a nearby star. These speeds were obtained with chemical rockets, fundamentally the same technology as rockets used by the Chinese 800 years ago. Both burn chemicals in a confined space to blow hot gas out a nozzle. We know it's possible to do much better. In the late 1950s, the top-secret Project Orion aimed to build a nuclear pulse rocket that could reach the stars in a human lifetime. This design uses a series of controlled nuclear detonations behind the vehicle to propel it forward. In 1968, Freeman Dyson calculated that a nuclear pulse design like Orion could achieve 10% the speed of light, 17,634 times faster than Voyager. At this speed we could reach the nearest star in 43 years. But Orion would cost hundreds of billions of dollars, 10 times more than the Apollo program. Moreover, the 1963 Partial Test Ban Treaty prohibited nuclear detonations in space. Project Orion was cancelled in 1964. Since then, we've found better ways of reaching the stars. One of those ideas is the star chip. The miniaturization of computers allows fully functional spacecraft, complete with cameras, sensors, controllers, and antenna to be built on a computer chip. The entire craft could weigh less than a gram. Owing to its size, it could reach 20% the speed of light, accelerated by a collection of ground-based lasers. Plans for the star chip were made in 2016. If they follow through, we could reach the nearest stars by 2050. Once built, the system can launch thousands of the star chips. It would take the lasers only about 20 minutes to accelerate each star chip to 20% of the speed of light, 60,000 km per second. At 10% the speed of light, self-replicating von Neumann probes could cover the galaxy in 1 million years. These time scales are large in human time frames, but they are small on evolutionary scales. If Earth is an indication, it takes about 5 billion years to evolve a technological species, but only 1 million years, 0.02% that time, for that species to fill the galaxy with its technology. On evolutionary time scales, the galaxy is accessible. Earth itself has lapped the Milky Way 18 times in her history. Given ample time, the bigness of space is no barrier to a technological species that wants to fill the galaxy. With a 1.7 billion year head start, technological civilizations have had plenty enough time. If space is not too big, the mystery remains. Why don't we see clear evidence of anyone's presence? Assuming intelligent species arise and last, then only two explanations are left. They either universally decide not to spread outward, or they do spread outward but remain hidden. They leave our universe. At some point aliens might discover technology that allows them to leave the universe, to transcend their physical existence, or perhaps even to create and explore realities of their own choosing. Traveling from star system to star system would become repetitive, tedious, and given the time scales, would be immensely boring. Having the technology to explore infinite possibilities from their own home, advanced civilizations might quickly lose interest in exploring outer space. This solution to the Fermi Paradox is known as the transcension hypothesis. But is leaving the physical universe possible? Leaving the universe is possible in a figurative sense. When someone is deeply engrossed in their device, or a computer game, they are in a sense in their own reality. Future virtual reality technology will make this truer still. Given the exponential progress of computing technology, getting ever smaller, denser, and faster, it may soon be possible to live in virtual reality. The best physically possible computers, those of the greatest speed and storage capacity, look little different from a black hole. To perform a computation, matter would be dropped into the hole in a specific pattern, The whole would perform the desired computation and return the result via Hawking radiation. Black holes are in a sense detached from our universe. If an alien civilization builds black hole computers, and if they put themselves into virtual reality programs run on these computers, then in a very literal sense such a civilization will have physically left our universe. They would no longer be part of our spacetime, and would live in a designer reality that's effectively causally isolated from our universe. According to the Kardashev scale, technological civilizations advance by consuming ever more energy. The energy of their planet, their star, and eventually their galaxy. But maybe we got it wrong. The Barrow scale proposes that civilizations should be ranked according to their mastery over the smallest scales. Level 1 manipulates objects on its own scale. Level 2 manipulates genes. Level 3 manipulates molecules. Level 4 manipulates atoms. Level 5 manipulates atomic nuclei. Level 6 manipulates subatomic particles. Level Omega manipulates spacetime structure. The smaller we can miniaturize technology, the faster and more efficient our computers become. Instead of exploding outward across the galaxy, civilizations might explode inward towards ever smaller dimensions. Quote: If the transcension hypothesis is correct, inner space, not outer space, is the final frontier for universal intelligence. Our destiny is density. End quote. John Smart. Exploring reality with computers offers many benefits over exploring space with rockets and telescopes. Unrestricted access, simulation lets them explore realms they can't get to physically. Such as past and future epochs, regions beyond the cosmological horizon, even other universes having different laws. Provides faster answers. With a fast enough computer, they could simulate the entire billion-year evolutionary history of a planet in hours, rather than wait billions of years to watch it unfold. More efficient, vast amounts of energy are needed to accelerate even a small object to a fraction of the speed of light. That energy could be much better spent on CPU cycles. In a space exploration, the inner space of consciousness is just as infinite and rich as outer space, if not more so. Virtual reality can provide any possible experience, the only limit being imagination. Exploration of inner space might even be the meaning of life. The transcension hypothesis's answer to why we don't see evidence of technological civilizations is not that they don't exist or that they universally destroy themselves, but that they have miniaturized themselves. Accordingly, they remain undetectable to our current technology. They are here. Perhaps life and intelligence are common and they do spread throughout the cosmos. Even if a technological civilization transcends and miniaturizes, there are still reasons it might spread. Chief among them is that it provides redundancy. Should a gamma-ray burst or other astronomical calamity befall them, being spread out ensures their continued survival. A technological civilization might also spread to protect itself and others. For example, to guard against the rise of malicious self-replicating probes, which if left unchecked could destroy all life in the galaxy. Finally, a technological species might choose to protect planets harboring life, so that primitive life might enjoy the same chance to grow and develop as that alien species did before them. Given the trajectory of increasing miniaturization of our technology, like our 1-gram spaceship on a chip, we can now envision alien technology that has mastered the nanoscale. To us, such alien ships might look like a grain of dust, but it would be a dust imbued with intelligence. The nanoships could contain a powerful AI or even the uploaded minds of billions of members of their race. Given the physical upper bounds on computer technology, an entire civilization of 100 billion souls could live on a single computer that is smaller than a grain of sand. With control over matter at the finest scales, such a civilization could easily make many copies of these ships and be present everywhere in the galaxy. Each ship could carry a complete set of every member of that civilization. Being so small, millions of civilizations could each have their own dust ships present in every star system of the galaxy. We would not be aware of them unless it was their desire to make their presence known. If this technology is possible, they may already be here, hiding and watching. Earth is protected. If they are here, why haven't they announced themselves? How could the potentially millions of independent civilizations all agree to keep mum? One possibility is that there is some form of galactic law, like the Prime Directive of Star Trek, which forbids external interference with a developing civilization. Another possibility is a convergence of ethics, a common wisdom shared by advanced civilizations that leads them to reach similar conclusions regarding what is right and wrong. If there is a disagreement, they could simulate outcomes of different courses of actions on computers to see what is the right thing to do. The older, more established, and more advanced civilizations could share their knowledge and experience with the younger and perhaps more rash civilizations. Young civilizations are apt to make mistakes, like launching self-replicating probes without the proper safeguards or interfering with the development of life on a young world by not following decontamination procedures, or making first contact with a civilization that's not ready. If anything like this is true, that would make our solar system a kind of nature preserve, or a zoo. Accordingly, this solution to the Fermi paradox is known as the zoo hypothesis. Conclusions? In this article we have reviewed our understanding of the development of life in the universe, and why it should be common. Our efforts to find evidence of life and intelligence. The current lack of definitive findings. To estimate how near the closest intelligent life is, we must rely on the Drake equation. Even with pessimistic assumptions, such as 1% of habitable zone planets developing life, and just 1% of planets with life developing intelligence, we still expect tens of thousands of technological civilizations having arisen in our galaxy over the past billion years. If just one of those civilizations survived its period of technological adolescence, it could in a very short time spread throughout the galaxy. But we see no evidence of this. Hence the paradox. Whenever we encounter a paradox, two things which can't both be true, it's almost always a sign that one of our assumptions is wrong. The Fermi paradox rests on two assumptions. 1. Technological civilizations should have arisen many times. 2. If there are other technological civilizations, we would see them. For the first assumption to be wrong, intelligent life must be unbelievably rare, so rare it verges on the impossible, appearing on 0.00000000000000000000000001% of star systems. It is possible intelligent life could be so rare, but it is also possible that the second assumption is wrong. Fermi and others at the time assumed that if intelligent life has arisen before, there would be obvious signs of it. Surely they would build great power plants out of their sun, conquer the galaxy terraforming planets, and travel the galaxy in huge generation ships, all while communicating by radio. We've seen the many reasons to doubt this. Aliens could easily be so alien we failed to notice them. We can already imagine that by miniaturizing and merging with technology, alien civilizations could become so small as to be practically invisible. And this is still from our limited 20th century human perspective. We have no concept for how an alien civilization in their 1 millionth century might look. We know not how they spend their time, nor what values guide them. We don't even know if civilization is the proper word for what they become. For all we know, intelligent life may merge itself into a singular superconsciousness. Perhaps all intelligent civilizations cooperate, as a single nation of intelligent beings. One thing is clear, our knowledge regarding behaviors of far advanced species is lacking. We know only that we don't know enough to settle the Fermi paradox today, but perhaps we can progress by reframing the question. What's more likely? That each of the 10 sextillion other chances intelligence had to arise failed, or that humans once showed a narrow imagination for just how different future civilizations might be.
This has been another episode presented by alwaysasking.com, where we ask the big questions. Thanks for listening.